Section 10.6 is about segment lengths in chords. To begin, let's start with another vocabulary word. When two chords intersect in the interior, so the inside of a circle, each chord is divided into two segments that are called segments of the chord. This new vocab word brings us to our first theorem, Theorem 10.14. It's called the segments of chords theorem. It states if two chords intersect in the interior of a circle, just like in the diagram, then the product, which means to multiply, of the lengths of the segments of one chord is equal to the product, again, which means to multiply, of the lengths of the segments of the other chord. So again, referring to the diagram, you see two chords that are intersecting on the inside of the circle, and according to this theorem, this part times this part is equal to this part times this part, just like it states right here. Let's apply this theorem in our next example. So here's example number 1. Find the measure of RT and SU. So notice that we have two chords that are intersecting on the inside of the circle. So according to Theorem 10.14, this x plus 1 times this 3x would be equal to this, the 4x, times this, the x. So let's set up that equation. So here's our equation. Again, we just took the two segments of the chords and multiplied them together. So I took 3x times x plus 1. Notice that I put parentheses around the x plus 1. And then the x times the 4x for our second part of the equation. So to start, we'll distribute the 3x. So 3x times x is 3x squared. And 3x times 1 is 3x. And we'll just simplify the second part of the equation and take x times 4x to get 4x squared. So the next thing I'll do is subtract this 3x squared over. So I'll end up with 3x equals x squared. And then I'm also going to subtract the 3x over, so I set it equal to 0. So I have x squared minus 3x. Now thinking back to Algebra 1, we have to do a zero product property here. So again, I just set it equal to 0. And now I need to turn the right-hand side into a product by taking out the greatest common factor. So I'd have 0 equals, they both have an x, so I'd have x times x minus 3. Now that I have a product set equal to 0, I'll take each one of these and set it equal to 0. So x equals 0 and x minus 3 equals 0. So my first answer is x equals 0, and my second answer is x equals 3. But if we think about this, x is equal to this little bit. So since a segment cannot be equal to 0, I'm going to toss out my first answer of x equals 0 and know that x equals 3 must be my answer. But remember, it asked to find the lengths of RT and SU. So then I'm just going to plug it back in. So if x equals 3, 3 plus 1 is 4, so this little bit is 4. And then x equals 3, so 3 times 3 is 9. So RT would equal 13. And then for SU, we know again that x is equal to 3, so this little bit right here is 3. And then 4 times 3 is 12. So SU would be 12 plus 3, which is 15. So the two lengths would be 13 and 15. Next, let's talk about a couple more vocab words. The first one is called a secant segment. It's a segment that contains a chord of a circle and has exactly one endpoint outside of the circle. So thinking back to before when we had just secant lines, it was a line that goes through the circle in two different places. Now we're shortening this up into just a segment. So a secant segment would have one endpoint on the circle and one endpoint outside of the circle. So again, it contains one chord within the circle. The part of a secant segment that is outside the circle is called an external segment. So this is labeled in the diagram as well. So here's your secant segment, and the part that is outside of the circle in the red here is the external segment. In a previous section, we talked about tangent segments, which just as a reminder here is a segment that has one endpoint on the circle and one endpoint outside of the circle. So remember, a tangent line hits the circle in one spot, so a tangent segment hits the circle in one spot and then has the other endpoint outside of the circle. And those new vocab words brings us to our next theorem, Theorem 10.15. It's called the segments of secants theorem. If two secant segments share the same endpoint outside a circle, so looking at the diagram, we have two secant segments sharing point E on the outside of the circle, then the product, which means to multiply, of the lengths of one secant segment and its external segment equals the product, again, which means to multiply, of the lengths of the other secant segment and its external segment. So now referring to the diagram, we see here that the two external segments are in red. So according to this theorem, EA times the length of the entire secant segment EB would be equal to EC times the entire length of the secant segment ED. Let's apply this theorem in our next example. So here's example number 2. Find the value of x. First, notice that we have two secant segments intersecting on the outside of the circle and sharing the same endpoint. According to theorem 1015, the length of 3, the external segment, times the entire length of the secant segment, which would be x plus 3, would be equal to the external segment of the other secant segment, which is 4, times the entire length of the secant segment, which in this case would be 6, since 4 plus 2 is 6. So let's set up our equation. So according to theorem 1015, again, the length of the external segment of our first secant segment, which is 3, times the entire length of the secant segment, which we said was x plus 3, is equal to the length of the external segment of the other secant segment, which is 4, times the entire length of the secant segment, which would be 6. So the first thing I would do is just simplify. So let's distribute. 3 times x is 3x, 3 times 3 is 9, and 4 times 6 is 24. So then I would just subtract 9 from both sides. So I'd have 3x equals 15. Divide both sides by 3. So x equals 5. Our last theorem is theorem 1016, segments of secants and tangents theorem. If a secant segment and a tangent segment share an endpoint outside of a circle, so looking at the diagram, we have a tangent segment and a secant segment sharing point E. Then the product, which means to multiply, of the lengths of the secant segment and its external segment equals the square of the length of the tangent segment. So again, referring to the diagram, we would square the length of the tangent segment, which is EA squared, which would be equal to the length of the external segment of the secant segment, which is EC, times the entire length of the secant segment, which is ED. We'll apply this theorem in our last example. So here's example number 3. Use the figure to find the length of segment AB. So notice we have a tangent segment and a secant segment intersecting on the outside of the circle and sharing point C. So according to theorem 1016, the square of the tangent segment is equal to the external segment of the secant segment times the entire length of the secant segment. So our equation would look like this. 24 squared, because remember you're supposed to square the length of the tangent segment, is equal to 16, which is the length of the external part, times the entire length of the secant segment, which would be x plus 16. So all we need to do is simplify. 24 squared is 576, and then I would distribute the 16. So 16x plus 256. I would first subtract the 256 from both sides to get 320 equals 16x, and then divide both sides by 16, so you end up with x equals 20. But remember, we weren't just asked to find x, we were asked to find the length of AB. So, since AB is what x is equal to, since x equals 20, that means that AB is equal to 20. That's it for this section. Make sure you jot down anything you didn't understand that we can cover in class before we move on, and we'll see you then.